Exercise 2326 is asking us to do a synthesis, and they say specifically to be sure to count the carbon atoms as you look from the molecule on the left to the molecule on the right. So let's do that. They both have these 6-membered rings, so that isn't a difference. In the carbon chain on the left, we have 1, 2, 3 carbons. Notice that that's just a bond to a bromine, not another carbon. On the right, we have 1, 2, 3, 4 carbons. So we need to add a carbon. Now we have a leaving group here, so we could do an SN2 reaction. And we know a way to make a strong carbon nucleophile. The first thing that might come to your mind might be a Grignard reagent. The problem is, if you use a Grignard reagent, let's say you treated this first with methyl magnesium bromide, so that this carbon would act as a nucleophile and displace that, the result would be, after that, you would replace the bromine with your methyl group. And the problem with that is there's nothing reactive there. We need a pi bond between these two carbons, and right now we don't have any way to get it. So although that using this Grignard reagent does get us the right number of carbons, it doesn't get us the pi bond that we want. Now there's another way we've learned to add one carbon onto a carbon chain. And usefully, this carbon comes with a functional group that allows us to transform it into other functional groups. That was sodium cyanide. So if we treat this with NaCN, the Cn, that's a triple bond between a carbon and a nitrogen, the carbon has a full negative charge. It can attack this carbon and kick this leaving group off to do an SN2 reaction. And what you'd have at the end of that would be one extra carbon here, triple bonded to a nitrogen. So if we're just thinking in terms of carbons, now we have 1, 2, 3, 4 carbons. It's true we have a nitrogen, that definitely needs to go away. But wait a second, that definitely needs to go away. You mean we would have to eliminate this nitrogen from here? Eliminate a nitrogen? Well, if we have an amine, then we can do an elimination, and when you do an elimination, you create a pi bond. That's what we just saw in the Hofmann elimination. But you need an amine to do that. Can we turn this into an amine? We can. First, use excess lithium aluminum hydride, right? Because when you turn this into an amine, you're replacing bonds to this electronegative element with bonds to hydrogen. So you reduce the number of bonds to the electronegative element. You use a reducing agent. So excess lithium aluminum hydride always followed by a water wash. And that will turn that nitrile into an amine. So these hydrogens that have added on here have come from the lithium aluminum hydride and the water. Okay, let me redraw this. Draw this in a slightly different way, because most of it is in the skeletal structure, but I have that weird carbon at the end. So instead of the carbon, I'm just going to have a dot, like a change, and the nitrogen will be here, so NH2. So this structure is the same as the one below it. So you can see you'd have 1, 2, 3, 4 carbons in each one, and then the nitrogen on that 4th carbon. Okay, so I'm going to erase this one, just to make it a little clearer. We have this. Now how can we get from here to our product? If you notice, the nitrogen goes away, and a pi bond is made. Those are the signs of an elimination reaction. We want to do an elimination reaction and have the nitrogen be the leaving group. That's a Hofmann elimination. So all you'd have to do is add excess methyl iodide. That would turn the nitrogen into a quaternary ammonium salt that can act as a good leaving group if you pry the iodine away that stabilizes it with silver, and then the oxygen in the silver oxide can combine with water to create hydroxide. If you heat it up, that will do the elimination reaction. So this sort of gives you a sense of how you should, it's often clearer to think of what the product will be or how to use a reaction when it's only one step. But this exercise gives you a sense of how to combine what you learned in the Hofmann elimination with other steps. Now, anytime you see a pi bond, you want to think, I can make that from an amine. And how can you make an amine? Well, we know several ways, but one of them is by reducing a nitrile. And you can get a nitrile, you can create a nitrile by doing an SN2 reaction with a cyano group. So you'd see, you can work this either way. We just thought of it backwards. You can think of it forwards too. You see a bromine, that's a leaving group. You notice you have more carbons in the product than you do in the reactants. So you can add a carbon using the a cyano group. Then you notice the nitrogen has to leave, has to go away. That would remind you of the Hofmann elimination. So first you have to turn this nitrile into an amine by reducing it, and then you do the Hofmann elimination. So you can think of this from many directions. These multi-step synthesis problems are sometimes a little tricky because they're not linear. You can approach them in many ways. They're multidimensional and they require critical thinking, but it's a matter of making connections between otherwise separate pieces of information that you've learned in order to be creative, to create a new molecule. But the new thing here is whenever you see a pi bond now, think you can make it using the Hofmann elimination starting with an amine.